Hello, everybody. This is for the course at UNSW, MATH2099. I'm going to go through the solution of 23. This is related to about the coordinate vectors of a vector in a vector space. Okay, we would like to find the coordinate vectors of this vector with respect to the basis given by these vectors in R3. This is our question. Before I start to going through the solution, I would like to remind you what is the coordinate vector conceptually means, what that means. So the coordinate vector, this is any vector, v1, v2, v3. These are basically the coordinates. With respect to a standard basis means that standard basis in R3, as we know, is E1, E2, E3, say 1, 0, 0, 0, 1, 0, 0, 0, 1. That's well known. We know that. So coordinate vector of this with respect to standard basis means that this vector can be written as a linear combination of these vectors. So exactly the same idea, coordinate vector with respect to the other basis elements, exactly the same idea, right? It means that the coordinate vector with respect to the base B will be the linear combinations of these with respect to basis B, right? We have, if this number V1, V2, V3, then this is V1, E1 plus V2, E2 plus V2, E3. That is a linear combination. Here, V1, V2, V3 are real numbers in real numbers, right? These are the coordinates with respect to standard basis. If we have these vectors, but then we will be able to write it down V1, V1, V2, V2, V3, V3. But in this case, of course, this is not equal to that one. These numbers will be different from this number, because this is just directly, it's coming from here. This is just one. So this is completely V1. So this will be a bit different from that. So there will be other numbers if you want to write it down this in terms of E. Like this will be equal to, sorry, this will be equal to maybe W1, W2, W3. There will be other numbers for this equality with respect to the standard basis. Okay, that's what I'm trying to say. The numbers will be different, but they may correspond to the same vector. Let's have a look. Let's do this calculation. So this means here, with respect to standard basis, this is like minus 8 E1 plus 6 E2 plus 9 E3. But we would like to find out the coefficients when we write it down as a linear combinations with these vectors. We would like to find out the scalars or the coefficients such that this equality satisfies. So these are the basis elements, and this is the vector. This is the coordinate vector with respect to the standard basis. I'm just going, we don't need to write it down standard basis, but just would like to remind you, this is the coordinate matrix with respect to standard basis. Now we would like to find out a vector, which means V1, V2, V3, find out their scalars such that that will be a linear combinations of the bases. Okay, now this is a linear system of equations, and the unknown vector is V1, V2, V3. All right, and the coefficient matrix is this vector and this vector and this vector. On the right-hand side, the B vector is minus 8, 6B. And if you do the row operations, I'm not doing this from here to here. There are several steps, but use some computer aid or whatever you like. From here to here, move on. And then you will be able to get the augmented matrix to reduce the echelon form as identity matrix here, which was 1, 1, 1 on the diagonal and zeros elsewhere. then you will have 2 minus 5. This means that V1 is equal to 2, V1 is equal to 9, V2 is equal to 2, V3 is equal to minus 5. So this vector is the vector with respect to the basis B. This is the coordinate vectors of this vector with respect to the B. Now, let's do such things in the space of the polynomials. Now, PT is the polynomial, this polynomial, and the B is this polynomial. These are 4 polynomials here. And you know that the standard basis of P3, right? P3, standard basis of the P3 is really 1t squared t cubed. Right? This is a standard basis for P3. Every polynomial can be written as a linear combination of these ones. It's dimension 4. Yes, P3 has dimension 4. Now we would like to write it down, this polynomial, coordinate vector of this polynomial with respect to the basis B, this one. This is basically the coordinate vectors with respect to the standard basis. As you see, this is a coefficient, a scalar times 1, another scalar times t, a scalar times t squared, a scalar times t5. If you want to write it down like the column vector, this will be like 8 minus 9, 3, 5 as in terms of the coordinate vector in terms of the standard basis. Our aim here even, well, in this case, B is this polynomials, and we would like to write it down P in this format for some alpha, beta, gamma, delta in the real numbers. So basically, we would like to solve this equation system. Unknowns, alpha, beta, gamma, delta. And yeah, as I mentioned in my tutorial, that it is easier to concentrate this correspondence between vector spaces in this case. To simplify computation, use the one-to-one correspondence between vector spaces. And this vector space is isomorphic to this vector space as vector spaces. So the polynomial, by just taking the coefficients of the polynomial, we can obtain A0, A1, A2, A3. You can change the order. You can take the another correspondence by changing the inner order, but this is the most natural one, and it is less confusing one, of course, and we can do the calculations. Okay, that's what we need. We just find it. This is P, alpha, beta, gamma, delta, P1, P2, P3, P4. So this equation implies that you can rewrite just by using this correspondence, or you can figure it out, right? You can open this up equations and make the constant term on this side is equal to constant term in this side, coefficient of this t equivalent to coefficient of t in this side, and you can go through that calculation. That's perfectly fine if that's what you want to do, but also you can write it down the matrix directly by using this correspondence. What I mean by that, so this is the polynomial -1 plus 2. So the coefficient A2 is 0, A3 is 0. So as a vector, this will be -1, -1, 2, 0, 0. So this is the first column, -1, 2, 0, 0. I think in that way I can take these two into the vision. So this vector, this polynomial in the vector form will be 1 minus 3, and the coefficient of t squared is 0, and the coefficient of t cubed is 1. Here, this polynomial will be 0, coefficient of t squared, coefficient of t cubed, which is -2. Here we have the constant term is 1, coefficient of t is 0, coefficient of t squared is 2, coefficient of t cubed is 1. So this is P1, P2, P3, P4, and these are the coefficients of these polynomials. And then these ones multiply with these alpha, beta, gamma, delta, which are the unknown vectors. And on the other side, we have 8 minus 9, 3, 5. You can check it. You can check from here to here how to get it. Open this polynomial out and make sure that you have this. And make yourself clear about these steps, right? Believe in me. This is equal to that one. It is crucial, of course. I'm writing down this on the column, right? If you have any doubt from here to here, how I passed, check it by yourself, just to make sure that it is clear, it is okay for you. Okay, just solve this equation system, and then you will be able to find reduced row echelon form, and this reduced row echelon form gives you the unique solution, which you will have minus 9, minus 4, minus 3, 3, sorry. So we can write the polynomial p as minus 9, minus 4, minus 3, plus 3. So this vector here is the coordinate vector of p with respect to the basis p. In terms of matrices, not much different. I mean, the concept as a coordinate vector is the same. The correspondence may be a bit different. Again, we have a matrix, one matrix, and we have another basis. And we would like to write it down this matrix in terms of this basis, which means that coordinate vectors, we would like to find out the coordinate vector of M with respect to the basis B. So this matrix is written in terms of the standard basis element. And standard basis element of the 2 by 2 matrices is just corresponds the position, like this position 1, all the others 0, this position 1, all the others 0, and so on. It's similar to the standard basis element in R4. And okay, that's it. So I just would like to say this is X, this is Y, this is Z, this is T. I'm just giving a names of these matrices so that I can set it up my problem. What is my problem is that I would like to find a solution such that M is equal to some coefficient, some scalar times X, some scalar times Y, some scalar times Z, some scalar times T. So I would like to find out alpha, beta, gamma, delta, satisfying this equation, satisfying this matrix equation. Again, as I've done in the polynomial vector space case, I will use a one-to-one correspondence between the vector space M22, which are 2 by 2 matrices over R, and the vector space R to the 4. This has dimension 4 because you have 4 parameters, right? 1, 2, 3, 4. And this is isomorphic or equivalent to R4, one-to-one correspondence. Again, this is the most natural way, A, B, C, D, A, B, C, D. You can choose another order here, which will give you another correspondence, but you need to be consistent in the same question. If you mix things up, then you will find incorrect result. By using this correspondence, again, we will be able to, for this matrix, will be in the column way, will be 1, 0, 2, minus 4, right? I'm going this way, A, B, C, D. So this is 1, 0, 2, minus 4. 1, 0, 2, minus 4. This is the 1. This is the first column. That's the second matrix, second column. This is this matrix, minus 1, 2, 1, minus 2, this column. And this is 1, 1, 6, 0. This is 1, 1, 6, 0. And then on the right-hand side, I would like to have 4, minus 5, 2, 6. So I would like to find out the solution of this linear system of equations. From here to here, we apply the row operations, find out the reduced row echelon form, and you will obtain an identity matrix here, which means that we will find a unique solution. So this is the unique solution for this equation system. Alpha is 3, beta is -2, gamma is -4, and delta is 1. So this vector is the coordinate vector of M with respect to the basis B. You can go back to your matrix form if you like, but M, it can be written as 3x minus 2y minus 4z plus t. So this is the coordinate vector of M with respect to the basis B. For the part D of this question, this is a little bit general in a sense. In this case, we have a general vector, B1 and B2. We want to find out coordinate vector of B with respect to the bases 2, 3, 3, 5. It means, this question means we want to find out alpha and beta scalars in R satisfying B vector is equal to alpha times one of these bases plus beta times one of these bases. So you would like to find out the solution of this linear system of equations. So you have two unknowns and you have two equations. So the augmented matrix will be 2, 3, 3, 5, and we have B1 on B2 on the right-hand side. Just applying the row operations. So I want this position 1. This is why I divide 1 over 2. And then I want this position 0. So this is R2 minus 3R1. And that gives me these numbers. And then I want this position 1, which means I need to multiply this by 2. That will give me 2B2 minus 3B1. I want this position 0. So if I multiply this row by minus 3 over 2, add to this row, I will obtain this equal to 0. In this case, on this side, I will have the identity matrix, 2 by 2 identity matrix. I have this one here. And if you figure out this minus 3, you're multiplying this with the minus 3 over 2 and adding to B1. That's B1 over 2. I just realized that this is B1 over 2. As you realize, this is B1 over 2, just incorrectly passed through here. So this is why I have B1 over 2 here. And organize that, we will be able to find 9, 10 B1 over 2 will be 5. So 5B1. Here is a minus 3. So that's minus 3B2. So what we have here, this is alpha, this is beta. So B is alpha times this vector plus beta times, which is that guy is times this vector. So this vector here, this and this, is the coordinate vector of B with respect to the basis B. So this is my shortcut for with respect to. I think this is clear for you. Yeah, that's all for this question. I hope it is useful for you. Thank you very much. See you in the next one.